All right, folks, so we can go through questions that you might have from the old test. I know a number of you have questions. The test is 43 questions long, or 42, something like that. So it's about, 1.5 times your regular test. And it covers all topics. So basically, I've gone through and I've looked at all the questions, and I've changed them a bit. Now, it won't be exactly the same as what you've seen on the previous quizzes, but it'll be the same material. So, for example, if it's a conservation of momentum problem, then that's what you'll have, is a conservation of momentum problem. So as you're going through the old quizzes, think about, well, what is the principle here, and how would I apply that to find other things? For example, like if it's a kinematics problem looking for the final velocity, then think about, well, I can maybe be looking for the displacement as well. Is that clear, what I mean by that? But if there's a topic that's not covered on the quiz, then it won't be on there. Now, for example, though, like if you have a standards question, like a standards of measurement, in fact, I've done this where I asked you about one standard, I can ask you about another standard. You understand what I mean? Like, what is the standard for the meter or whatever? I could also ask you, what is the standard for a second, or something like that. All right, so it's sort of broadly encompassing. I just want you to be prepared for that. It's not going to be exactly the questions that you saw in the previous quizzes. But those are good questions for you to practice. All right, you have questions sort of about the format of the exam? You didn't take a call?
No, that was my email. I was busy on customer.
Oh, okay. That's okay. Okay. All right. Well, all right. How about I have quizzes, so if you're here and you don't have your quiz, just see me afterwards. I'll give it to you. All right. Questions about the old test? Matt?
Yeah, on quiz 1.
Mm-hmm. Mm-hmm.
Particularly on that car tile, the car tire roll.
Okay. What problem was that?
It's number 4 on quiz 3. You can draw it out.
Yeah, so when a car's tires are rolling, which of these is the type of friction between the road and the tire? Static friction occurs when you have two objects that are not moving with relation to one another, so they're static. And kinetic friction occurs when they're moving, right? Kinetic means motion. Well, with the car tires rolling, it seems like they're moving, but the surface of the tire with relation to the road is not moving. So if I have a car tire here, it's rolling in this direction, and then the road is there. At any moment, the surface of the tire and the road are stationary with respect to one another. It's only if the tire stops moving, that if it stops rotating and it skids, that's when the surface of the tire is moving, when kinetic friction is relevant, is if the tire locks up, if it stops rolling. Is that clear? So anytime you have two surfaces that are moving with respect to one another, that's kinetic friction. And anytime you have surfaces that are not moving, then that's static friction. The tire is rolling, right? But the surface of the tire and the surface of the road are stationary with respect to one another, because the surface of the tire isn't sliding across the surface of the road. It's only when that tire stops rolling that the surface of the tire skids across the road. All right? What else? I'm going to go back to quiz 1, and we'll just sort of go from there. All right. Any questions about quiz 1? You will have to do dimensional analysis. You will have to do estimations like this. You will have to do trig, standards, significant figures, all this stuff. Obviously, you'll have a graphing question, something similar to this. You will have to interpret motion graphs like this. You will have kinematics questions as well, something similar to these. Evan? Yeah. So this one followed up to number 10. By the way, on the quiz, I've written all the questions so that when you use G, you just use G of 10. it makes your math a lot easier. So a lot of the math is really simple. Let's see, for the man in the previous problem, how far does he travel in 10 seconds? Remember, I have two kinematics equations. I have the y equals v naught t, that's 1/2 at squared, and then I have v equals v naught plus at. I don't give you those equations, but if you look at your equation sheet, I give you the equations for the rotational motion. Isn't that correct? Yeah, so they're basically the same. It's just you're going to translate your x into theta, v into omega, and all that jazz. So you sort of have those equations. They just have different variable names. Let's see. So I want to know how far he travels in 10 seconds. Since I'm looking for a distance, I'm going to use this one. V naught is 0 because he's jumping out of the space capsule, like the Red Bull thing that we watched in class. Remember that? He jumps out. So his initial velocity is 0. So this term just goes away. So this is just going to be y equals 1/2 at squared. And that's going to be 1/2. Our a is our acceleration due to gravity, 10 meters per second squared. And t is 10 seconds. That's 5 times 100. That's 500 meters. All right. There are some kinematics problems. They're pretty simple in this regard. The one thing you need to be careful of on the kinematics problems is that you're clear on what the sign of the acceleration is. So remember, if you're moving in a positive direction and you're slowing down, what is the sign of your acceleration? It's negative, right? I'm not going to tell you that it's negative, but you need to be clear on that. All right? What else from this? Is that clear, Heaven? That's it. There are several other, if you look back on some of the old exams as well, the other old exams, you can find other kinematics problems. But you'll see a couple of kinematics problems. Well, 3 to 4 kinematics problems tomorrow. What else here?
Number 12, because it's in that quadrant, the acceleration is positive, but it's slowing down, so the velocity is negative, right?
No, let me show you. So with this, when I have my x versus t, you want to look at the slope and how the slope is changing. So here, my slope is positive or negative? It's negative. So I have a negative velocity. And then you want to ask yourself, is it speeding up or slowing down? And so it's slowing down, right? Because I have a big slope here, and I have a small slope here. So I have a negative velocity, and it's slowing down. And then you go back and you remember that, well, if my acceleration and velocity are in the same direction, it speeds up. If they're in opposite directions, it's slowing down. So since it's slowing down, I know my acceleration is opposite that. So it's going to be a positive acceleration. All right? So that would be positive. Let's just try another one. Because there is, at least on one of your exams. I've written 2 exams today. So if I say that something's on your exam, it could be on either one, right? Because I have 2 classes. So if I say something is on the exam, please don't take it as definitive. It is on one of your exams, but I'm not sure which one. All right, let's take one that looks like this. Positive or negative velocity? It has a positive velocity. Speeding up or slowing down? All right, slowing, so the acceleration then is negative. It's opposite the velocity. Is that clear? Yeah, though if you have a velocity versus time graph, it's not going to be, it will be linear, all right? Because we generally deal with constant acceleration. It would be with something like this. Is the acceleration positive or negative? The acceleration is positive. If it looks like this, the acceleration is negative. There aren't any of those on either exam. All right? Y'all are okay on interpreting these position versus time graphs like this? We just sort of step through it right quick. If I ask you something like the average velocity, then you're just picking the points off. So remember, average velocity, go back to your definition. Average velocity is delta x over delta t. That's x final minus x initial. over my change in time. So for example, here I was going from 20 to 40. Right? Well, let's pick a different time. Let's say I want to know the velocity between, I don't know, 30 and 50. Then I just read off the final and initial positions. My final position is 10, minus my initial position, which is 40, divided by my change in time. That's going to be 50 minus 30 seconds. And so that's negative 30 over 20, which is negative 1.5. All right? So you're just picking off the data points. You're not actually looking at the lines in between. So notice I didn't take anything about this line in between. Heather?
What was the problem when you had to figure out area?
Yeah, I think that was a homework problem. It wasn't on in the quiz.
It's number 13.
Oh, is it 13? Oh, yeah. But since since it wasn't, we'll look at 13, but there wasn't a qualitative problem where you had to find the area, and so you won't see it on the final. But let's go look at 13, because it did come up there. Hey, Michaela. We had this V versus T graph, and asked which of these statements is false. And the statement that was false was that they all travel the same distance. And they don't travel the same distance because the area under a V versus T graph equals the distance traveled. Is this mic too loud? Y'all okay? It is too loud? Oh, it is. Okay. So anyway, the area, like for example, under the C graph is there, and so just a little distance. The area under the B graph is bigger, and then the car A travels the furthest of all because it has the biggest area. They all have the same displacement, but they have different distances. You're right, they have the same displacement. Oh, actually, no. No, they don't have the same displacement. No. This isn't the position, this is the velocity. Yeah. But there are no qualitative things like that where you have to find the area under a graph. All right. So those were chapters 1 and 2. Anything else from this quiz? We can come back to it. I think the class did the worst on this quiz of any of them, but I thought it was the easiest material. Is that right? Usually the first quiz is just sort of a... Yeah. Well, let's look at quiz 2. Quiz 2 is probably, probably the hardest. Quiz 2 and 3. The hardest material. This is going to be 2D motion and vectors. Yeah. All right. So you want to find the x component. And if you don't see an explicit question like this, it'll certainly come up in some of the other questions. So you need to know how to find the x and y components because it comes up a lot in various things. I have a vector with a magnitude of 25 meters. So this is 25 meters. And it has an x component of 12 meters. And I want to know what is this angle. So anytime I'm talking about x and y components, I draw a right triangle. The x and y components are perpendicular to one another, and the hypotenuse is the magnitude of the vector. So I have a right triangle here. I know that the cosine of theta is adjacent over hypotenuse. That's 12 over 25. And so theta then is the inverse cosine of 12 over 25. Right. Be careful, watch that, because, like, what if it was the, I don't know, what if it was, how can I change that? I don't know. But if it was in a different quadrant, right? Yeah. Like, what if it was something like this? What if the, What if the angle, let's say 30 degrees below the x-axis, right? And the magnitude is equal to 10 meters, and I would want to know what is the y component, for example, right? So you need to know how to sort of work with these vectors in this way. And I always find it helpful to draw a picture. So it looks something like this. I'd have a vector that looks like this at 30 degrees, and I'd want to know what is this vector, the y component, right, which I can also draw over here. And so if I look at my right triangle, this is going to be 10. This will be my y component, and this angle will be 30 degrees. And then I could solve for that y component. But the y component will have what sign attached to it? It'll be a negative, yeah, because it's pointed downward. And so just make sure you read the words carefully, and that you always find it helpful to draw a picture. It is 42 questions long, so I mean, you're not going to have a lot of leisure time, like to sit back and drink a cup of coffee or whatever, but you'll have more time than you normally do. So just be careful in reading the questions. All right, what else in this test? Is this clear? It's an important question because it comes up a lot. All right. You'll have one of these vector questions. I think that should be a gimme, right? A gimme point? Yeah. There are some projectile motion problems. Each class has a projectile motion problem. Each one is different, but they're similar. Y'all okay on projectile motion? Yeah. Mm-hmm. This one is, yeah.
I was like, how, I know it's a success problem. When I got to the time for the supposed to be at the time, then we had to choose the do not use something like the problem.
Mm-hmm. Right. I mean, I don't understand what you're saying. So, there were two steps here, right? And first thing, you need to understand with these projectile motion problems that the acceleration in the x direction equals 0, and the acceleration in the y direction is minus 10. All right? So whatever velocity it has in the x direction, it's going to keep all throughout the motion because it's not accelerating in that direction. It's neither increasing nor decreasing. So this object will have 42 meters per second in the x direction all throughout the trajectory. All right? However, there's another velocity vector, the velocity in the y direction, that's down here. Now, at the very beginning, this v naught y is equal to 0, but it gets bigger and bigger as it goes along. It increases in speed. Right? So you need to understand those two principles, that I have these two components of motion that are acting basically independent of one another. Now, you need to get the time in this problem, and almost always you're going to need to get the time in the projectile motion problems, and then you'll probably have to get something else, like a velocity or a displacement. Now, in order to get the time, you're almost always going to use the y motion. Right? And so if I look here, I know that the y displacement is negative 500 meters. That's a half a kilometer. Right? It's starting up at 0 and it's dropping 500 meters. And then I know that my v naught y is equal to 0. And I tell you, that goes back, that's why that in that equation, that first term goes away. Because v naught y is equal to 0, this whole thing goes away. Because 0 times any number is 0. All right? And then I can find t. So I have y as 500 equals 1/2, excuse me, it was negative 500. 1/2 of negative 10, that's my gravity, times t squared. So that gives me t is the square root of 100, which is 10 seconds. All right, so that gives me my time, and that's going to be sort of the first step in these projectile motion problems. And then I could ask a number of things. Now here I asked, what is this distance, x, or d or whatever, to get to this point? And in order to find that, we say x is equal to vx times t. Now that's just this equation for the x motion, but since there's no acceleration in the x direction, that whole 1/2 at squared goes away. And I know vx, that's 42 times 10, so it's 420 meters. All right, I could also ask what is the velocity in the y direction? Right? And the velocity in the y direction would be v0 y plus ayt. So that's going to be v0 y, which is 0, plus negative 10, that's my g, times t. And that's where this 10 comes in over here, times 10. And so that's equal to a negative 100 meters per second. There are how many components to the velocity at this point? Are there one or two components to the velocity, the vectors? There are two. There's an x component, which is 42 meters per second, and then there's a y component, which is 100 meters per second. All right? What is the magnitude of the velocity at x? How would you find that? Is it greater, less than, or equal to 100 meters per second? It's greater, right, because you have 100 and you have 42, so you have to do the Pythagorean theorem, right, to find that resultant. Square root of 100 squared plus 42 squared. Yeah? Okay. I just expected more excitement about that, and y'all weren't really showing it. Okay. All right, can I clear this? There's I think one projectile motion problem, one calculation for each class. What else on this test? This also gets a little bit into chapter 4. Number 11. Okay, this is sort of a kinematics and a Newton's second law problem. We want to know the force. If I'm looking for the force, I know from Newton's second law that F is equal to m times a. So I need to find the mass, I need to find the acceleration. Now, I know the mass here, so I just need to find the acceleration. I have this information about the velocity changing in a certain amount of time. I can go back to my kinematics. V is v0 plus at. So and solve this for a. All right, so my acceleration is just my change in velocity or my change in time. That's 30 minus 10 divided by 10 seconds. 20 over 10 or 2 meters per second squared. Okay, so that's my acceleration, and now I can take that and plug it in here. So it's 1,000 kilograms times 2 meters per second squared, 2,000 newtons. There are some Newton's second law problems, both 1D and 2D. We can work through some 2D problems. I'm not sure they're on this test. Hey, Shana, come on. But some of them are just going to be simple, like F equals ma. This is the force, this is the mass, what's the acceleration? But others of them will be a little more complicated, kind of like this one. All right? I can do that, right? Yeah. Uh-huh. The acceleration due to gravity for the rock and the feather are the same, right? In a vacuum, they fall at the same rate. But because the stone has a greater mass, it has a greater force acting upon it. But the acceleration is the same, right? But, you know, F equals ma, right? So they can have the same acceleration but different masses, and then they'd have different forces. Now, obviously, like if you drop a stone and a feather, eventually the feather is just going to stop accelerating, right? Why does it stop accelerating, the feather? What happens to the forces that are acting upon it? It stops accelerating because of what? Air resistance, right? What happens to that air resistance for it to stop accelerating? It increases up to a point until it equals what? The force of gravity, yeah. So if I have this feather, if I can draw a feather. That's a feather. Now, it has a force weight acting on it, and then it also has a force due to the air resistance. When those two equal out, we didn't talk about terminal velocity, but that's when it reaches its maximum velocity. The air resistance comes to a point where it equals the weight. Is that clear? All right. There's some definitions there, inertia. Matt, did that answer your question? Yeah, okay. Let me make something clear here. This is a little bit different. It's still Newton's second law, but it was a little bit different, and you'll see it tomorrow and in the online section with both classes. Say I have two objects here, right? Say two masses, 1 kilogram and 2 kilograms. And I have some forces acting upon them. Let's say I have 10 newtons and 1 newton acting over here. How do I go about finding the acceleration of those? Well, these are attached by a rigid bar. What is the net force acting on those objects? The net force. What's the net force? What's the net force? You do know, actually. The sum of the forces, right? I have 10 newtons and 1 newton, so it's 9, right. So it's just 10 minus 1. So my net force is 9. Right? And what is my acceleration? That's what I want to know. Well, I know that F equals ma. Right? So which mass do I use? Do I use the 2 kilogram mass or the 1 kilogram mass? Or what? Use them both, right, because they're both accelerating. Right? So you would say 9 newtons equals 3 kilograms times the acceleration. So the acceleration equals 3 meters per second squared. You'll see a problem similar to that tomorrow. It's a little bit different, I understand. It's a little more different than I like to make them, but that's why I'm telling you about it now. All right? If I have two masses and they're both accelerating at the same rate and have these forces involved, you just treat it like a normal Newton's second law problem. You just take the combined mass. Is that clear what I'm saying? You have two different bodies of mass. They're moving at the same rate. Okay. What else? Is that it for now on this one? Okay, on dynamics like this, if I'm accelerating, like the elevator problem. Oh, yeah, let's just look at it. So if you have one of these where an object is moving up or down, the first step is just to label all the forces. Here I have the tension, and I have the weight. And then you just say sum of the forces equals mass times acceleration. Now the tricky part is if you make sure you get the sign right on the acceleration. You need to be very careful that you look at the direction. So you have Ft minus Fw. That's just the sum of these two forces equals the mass times the acceleration. And I'm looking for Ft. I'll just solve this for ft. Right, the weight is 10 kilograms times 10 meters per second squared plus 10 kilograms times 10 meters per second squared. All right, this is G, and this is A. They're the same, but they're not related. Okay, it just happens to be the same. It's accelerating upward at 10 meters per second squared. All right, so that gives you 10 times 10 plus 10 times 10 is 200 newtons. What if it was accelerating down at 10 meters per second squared? What would this be? Or what would the whole thing be? No, not 100. It'd be what? 0, right? Because it'd be 100 minus 100, so it'd be 0. That's free fall, right? If you're falling at the same rate of the acceleration due to gravity, that's being in space. That's why you're weightless in space, because you're constantly in free fall. You know, I heard recently that astronauts, like when they're on the shuttle or in the space station or whatever, that it's very difficult to sleep because you don't have forces acting upon you. And some people really like to lay their head on the pillow. Like, y'all like to lay your head on a pillow? But astronauts can't do that because there's no gravity. And so what they do is, some people who can't sleep without their pillow, they just strap it to their head. All right, what else? We'll move on to the next one. What was this? Oh, goodness. I just done quiz 2. Okay, quiz 3. All right, there will be an inclined plane problem. Let's just step through this. It'll be something similar to this. With your inclined plane, you want to draw your vectors. All right. I have my weight here, force weight, and I have my normal force. And then you want to draw your x and y axes. You draw them like that. You always draw the x-axis. That's the negative x. This is the positive x. With the x-axis parallel to the plane of the incline. And then you need to recognize that this angle is equal to 90 minus this angle. So that's 30 degrees. All right, so for any inclined plane problem, that should be sort of your first step. And then sometimes you won't need to really resolve all the vectors. You can just look at what's relevant. And in this case, we only really want to know about the x motion. There's no friction, so I don't need to know the normal force or any of that jazz. It's a pretty simple inclined plane problem. I'm just going to do the sum of the forces in the x direction. The sum of the forces in the x direction will be the x component of the weight. So that's going to be Fw cosine of 30. Let me draw this out over here. So I write out my vectors. I have an x component of the weight, that's Fw cosine 30. And then I also have a y component, Fw sine 30. My normal force. And then I have this other force, F. All right. Fw cosine 30 minus F is going to equal to the mass times the acceleration. And the acceleration is given. Now be careful here. The acceleration is up the plane. Is that going to be positive or negative? It's negative because it's in the negative x direction as we've drawn it. So I'm going to go and put some numbers in here. I have 2 kilograms times 10 times cosine of 30. 10 is my gravity, minus the force F, which is going to be what I'm looking for, equals to 2 kilograms times negative 5. So be very careful with that sign, okay? Because if you get the sign wrong, you're going to get an answer that's up there, but it won't be right, okay? And then we solve that for F. I don't know what it is, but... I don't need to solve it, right? Oh, okay. There is an inclined plane problem for everybody. Can I clear this out? No questions about the inclined plane? It's not going to be a terribly difficult one. No friction is something similar to this. Talia?
I was going to ask, is there anything other than what is probably
I could add friction to it, but largely it'll look like this, more or less. Right?
So if friction is added, how would you?
If friction is added, you have to find the normal force. Right, and you have to remember there is friction on the test,
Yeah.
but not on an inclined plane. But if friction is added, if you recall, the frictional force is equal to the mu times the normal force. And if friction is added, you have to find the normal force. The normal force is equal to the y component of the weight. And you're probably looking for mu or something like that, and you would find the coefficient of friction. But there's no friction on inclined planes on the test. That makes it a bit more complicated. Michaela? The friction always opposes the direction of motion. So for example, if we know that this is accelerating up the inclined plane, the friction would be opposite that. So if there were friction, it would be in that direction because it's always opposing the motion. Now, if it's static friction, I guess not moving, right? So, like for example, if I had this, it's like that. It wants to move down the inclined plane, so I know then that the friction is up the inclined plane. The static friction will be up the plane. You follow? Because I know that it wants to go this way, but I have a frictional force that's pushing up this way to hold it there. Not always, by Brett. I understand. Yeah, if y'all need to go, this is just help session, so it's very informal. Y'all come and go as you like. But now I'm going to tell you all the answers. Static and kinetic are always opposing the motion. But with static friction, it's not moving, so it opposes the tendency for motion. If it's moving up the hill, the friction would be down. If it's moving, yeah. Mm-hmm. All right? Is that clear? All right. What else here, guys? Any other 2D force type problems or frictional problems? That was chapter 4B. I don't know if you remember, we split chapter 4 into two pieces, those of you that are in the 3C section. Yeah? Okay. All right. This was a work problem. It was meant to be pretty easy, so I threw in this 200 newtons, which you didn't really need at all. It didn't really matter. That was just the weight. Although it was important for number. Oh, yeah, you were looking at number 12. I'm sorry. I thought you said 11. Yeah. So you want to know the normal force on the block? Good to draw your force diagram. All right, so I have a couple different forces acting. I have this force F, which is 60 degrees and 30 newtons. I have the normal force, and then I have the weight. This was a little bit different than ones that we had done because it had this additional force that was pulling up. But let's go ahead and draw our resolve vectors. I have Fn, F sine of 60, F cosine of 60, and Fw. And I know that the sum of these forces has to equal 0, and so I just set those equal to 0, and I solve for the normal force. It was difficult because the normal force wasn't equal to the weight. The normal force, I'll show you, F sine 60 plus Fn minus Fw, that's equal to 0. So if I solve from a normal force, it's going to be Fw minus F sine 60. All right, where F is this 30 newtons, and Fw is 200 newtons. So my normal force has been decreased. It sort of makes intuitive sense, I think. Like if I pull up on this object, the normal force decreases, to the point where if I pull it all the way up off the floor, it has no normal force. So if I just apply some force, the normal force decreases as I add more and more force until it goes to 0. All right? Does that answer your unstated question? Yeah. That was the big part of the problem, yeah. So a lot of people miss that problem. So you're in good company. All right. I don't recall if this was on the test. I think it is actually. I forget. I don't remember. Or something similar to it. All right. Also had work and energy here. You can see it's just sort of a basic work problem like this, FD cosine theta. That's not on your equation sheet. I know that y'all like to have the equation sheet for all the chapters, but that's not going to happen. But there aren't that many equations. It's really just sum of the forces equals ma, momentum P equal mv. And gosh, I think that's it. Isn't that it? Huh? Alpha. Oh, that's all on there. That's on the equation sheet. Chapter 7 is on there. Yeah. I'm pretty sure. All right. Or what else? Oh. You will see some momentum problems like number 13. Initial momentum equals final momentum. Impulse problems. Those are all very similar to your homework. You need to know what elastic and inelastic collisions are. Elastic collisions are where, just a second, Michaela, where both energy and momentum are conserved. I like to think of elastic collisions like really bouncy things are elastic, and when they bounce off of one another really well, then you conserve both energy and momentum. But inelastic are not bouncy things, like, I don't know, puffs of cotton or whatever. And those don't conserve energy, but they do conserve momentum. Michaela? Sure, what is it? Mm-hmm. Mm-hmm. So you had 4 balls. I think this was like in the homework. And they're all separated by, say, 1 meter. This is relevant. I mean, you will see moments of inertia of discrete particles. That's what this is. And it sounds like you're saying that you had an axis that went along through there, and you're looking for the moments of inertia as it rotates about that axis. Let's say these are all 1 meter. I don't know what it was on that, but something similar to that. Because these are on the axis, they don't contribute to the moments of inertia at all. Remember, moments of inertia, its basic definition is just the sum of mr squared. Right. We had different equations for moment of inertia. That's our basic definition, and we'll use this whenever we're using discrete particles. And then we have that table with all those different rigid shapes, the sphere, the bar, all that jazz. But anytime you're just dealing with a particle at a certain distance from your axis, it'll look like this. Okay. Yeah, you don't do that. All right. Sorry, that must have been a mistake. Now, in this problem, you have to use a little bit of right-angle trigonometry to find out what is this distance. We'll call that r. And you can do that. I mean, this is a right triangle right here. This distance is 1 meter. This angle is 45 degrees. So you can find r. Your moment of inertia problem, this won't be that convoluted. Okay, they'll be more straightforward. But there are some discrete particle moments of inertia, as well as like some rigid body type problems as well. Does that answer your question? Yeah. Do you have any others for you here? Okay. All right, folks, anything else from this chapter? Oh, goodness, that's almost 4 up. Anything else from this one? Okay, which one was this? Hi, Michaela. Let's look at quiz 4 then. Okay, this was our chapter 7 and 8. That was going to be kinematics, torques, moment of inertia, and angular momentum, all of which you'll see. Over. Next week. Any particular questions, Talia? Okay. Okay, you will see one of these. What's the net torque about an object?
Where you like do the problem.
Mm-hmm.
Or like how do you choose which
Forces to use?
yeah.
Yeah. Well, you want to look for this one. About point C, you only had one force that was causing a torque. You don't use this force because it's at the axis of rotation. And so the torque is equal to Fr sine theta, right? And F is equal to 10, theta is 40, but R is 0, because R is the distance from where the force is applied to the axis of rotation. So for that one, the torque equals 0. Now over here, the torque equals 0 as well, for a different reason. Torque is Fr sine theta. F is 5 newtons. R is 2 meters. That's this distance. And theta is this angle, is 180. And the sine of 180 equals 0. Or you could think of it as the sine of 0. That there's 0 degrees between the force and the moment arm, or 180. Either one would be correct, because the sine of 0 is 0 as well. All right, so then the only torque is offered by that one, and it's just 20 times 2, which is 40. And it is clockwise. No, because, well, we do it sort of, the sine of 90 equals 1. Yeah. Right, yeah. It's good to know that the sine of 90 is 1 then. Like, that's just something you can use, like, out in everyday life as you walk about. Go about life.
So say for instance, the one that got the sine of 180, if it was pointed downwards, like at an angle, then
you would use it, yeah. Like if it was pointed down instead, say it was like that. In that case, I would give you this angle, say it's 30 degrees or whatever, say it's 4 newtons. Then the torque, let's see, that is a clockwise torque. It would be negative because it's clockwise, and it would be 4 newtons times 2 meters times sine of 30. All right. Holly? Okay, I was just about to get into that actually. So, you know if it's clockwise or counterclockwise, I like to use a pencil. I just hold it up here, and I imagine this force pulling down, and it causes my pencil to move clockwise. You see? If I pull down on this, like this force would, it'll make it go clockwise. On this force, it pulls up. It also makes it move clockwise. All right. I think that's the easiest way. Just sort of imagine each individual force. What direction does it cause it to move? I have this force which is pulling down on the object, and it causes my pen to move clockwise. It pulls up on this side, which also causes it to move clockwise. The force vector is pointing up. Not following. Oh, because I just drew this vector right here. It's pulling down. Good. Well, this one's pointing up. Mm-hmm. Yeah. No, no, because if my not necessarily, like what if I had a mm-hmm. Yeah, so if I was looking at this red vector over here, that red force, it would pull down on this side. That would be a counterclockwise force. Yeah, this one. It would be a counterclockwise torque. Like if I pulled up on this side, it would make it go counterclockwise. Yeah, so there's no hard and fast. I mean, I guess you can memorize all of the various scenarios, but. Mm-hmm. Okay.
But no, I think what you're doing now is I was holding my finger like this.
Uh-huh. Yeah. Just hold it up on the paper. All right? Is that clear? Mm-hmm. All right. Can I clear this? Sure. Yeah. Okay, so I want to know the angular acceleration. All right, so I want to know what is alpha. All right, and I know that the torque equals I alpha. That's Newton's second law, right? F equals ma, but in a rotational frame. I already know the torque. It's 40. That was from problem number 10. I need to find I. This is a rod. So you'd look on that little chart, and you'd find that the moment of inertia of a rod or a bar is 1/12 mv squared. That's 1/12 of 3 kilograms. V is the length. So that's 4 meters squared. 1/12 of 3 times 16, 48. It's 4 kilogram meters squared. And then you solve for alpha at equal 10. I would expect to see a application of Newton's laws. That's what this is, Newton's second law in a rotational frame. I would expect to see something like that. We've seen that in different variations. Like another type of problem that you've seen like in your homework lab is if you have an object like a sphere or a disk or something, and you have a force applied to it. I think there was one on this test, actually. You know what I'm talking about? What's the acceleration or what is the velocity after a given time? All right, can I take this away? All right, what else from this chapter? Number 17. Okay, well, anytime you have a units problem like this one? But haven't you 17? Oh, really? Oh, like different classes, right? Oh. Okay. Oh, that's right. Is this my online section? This is my 3P section. All right, so I have this arm just balancing the torques, kind of like we did in lab. I want to label all my forces. I have a force here that acts up. I'm going to call this F bicep. And then I have over here another force. I'll call it FBB, the bowling ball. And I know that the sum of these torques has to equal 0, but I can just say that, well, this torque has to equal this torque. So that's going to be the force due to the bicep times the length of the moment arm. Since this is my axis of rotation, this is the length of my moment arm. So 0.03 meters. And that's going to equal the force of the bowling ball times this distance, which is 0.35 meters. And then I solve for the bicep. It's really big, actually, at 50 newtons. Is it 580? I think it's 580, isn't it? Yeah. So holding a bowling ball like that requires a force that's equivalent to like a person, small person. Yeah. Okay, is that clear on this? It's a torques problem, balancing torques. Oh yeah, that's clear. You asked this for Heather?
Is there anything that, like, other than asking one question, like, is there, like, something else that you can ask other than these questions? I know we had a question like this in homework.
Mm-hmm. That was basically the same.
Yeah, I confused with one.
Oh, really?
Maybe I read it wrong, but
The only other difference, I mean, in this one we assume that the bicep is perpendicular to the forearm. The only other caveat that you could throw is that what if the force due to the bicep looked something like that? And in that case, you would have to include this angle theta. So over here, we'd have a times sine of theta, like where if your arm was held out more like this. And I would be very clear about what that angle theta is. Because here, we're assuming, we're not writing sine of theta because it's sine of 90, and that's equal to 1. But it's always sort of assumed that it's there. All right. 14? I know some of you have to go. 15. Okay, these four wrenches have forces. Which experiences the greatest torque, and which experiences the least torque? All right, well, the least torque is going to be number 4. We have a couple of different things that affect torque. Fr sine theta. Right. So the one with the smallest moment arm will give us a smaller torque. So number 4 has a low moment arm, and it also is at an angle theta. And the sine of 90 is equal to 1, but the sine of anything less than 90 is less than 1. So as that angle decreases, then this gets smaller. This sine of theta term gets smaller. All right, you get maximum torque when the force is perpendicular to the moment arm. You measure it. Doesn't matter, actually. They'll come out the same. Doesn't matter. It doesn't matter. Like the sine of 30 is the same as the sine of 150. All right? But always measure the angle closest to the moment arm like that. So that's the smallest torque because R is small and theta is less than 90. The largest torque is going to be this one because it has a big moment arm and it has an angle that's perpendicular. Anytime you have a perpendicular force, that's going to give you maximum torque for that moment arm. And your moment arm is like a cheater pipe, right? I've used a cheater pipe before, like on a wrench. If you make your moment arm longer, then it provides more torque. Right. And for number 4, the sine of theta will be less than 1, some fraction, 0.8 or 1/2 or whatever. Right. And that's why number 2, the torque of 2, is less than the torque of 3. R is the same for both of those, but since theta is less than 90 for number 2, it makes that torque smaller. You always get maximum force when your torque is when your force is perpendicular to your momentum. Right. Mm-hmm. Well, it doesn't matter because this one gives us our largest torque because it's perpendicular. It's going to be this one because not only is it at an angle, yeah, because the moment arm is really short and the angle. Those two things combined. So it doesn't really matter what the angle is because those two are somewhere in between. Those 1 and 2 are somewhere in between. Okay, that's very important where it is. Yeah. All right. Can I clear this? If you forget, you can just pull your cheater pipe out of your backpack and you can think about that. In case you carry that around with you. All right, what were the other ones, Heather? Number 1, a lot of people miss that. That's not on this. Okay. Oh, yeah, let's see. The tension is greater than the weight. Wait a minute. I'm not sure, actually. Let me take that back. I'm not positive that it's not on there. So let me show you. I have a kid on a swing, going back and forth, back and forth. There are a couple of different forces acting on it. I have the tension in the rope, and then I have the weight. I know that the sum of the forces is equal to ma. That's ft minus fw. So look, this is my centripetal acceleration, ar. And so that's going to be mv squared over r. Right, because my tension is equal to my weight plus mv squared over r. Yeah, we did that one in class. Okay, now well, never mind, I don't want to muddy it up. Yeah, that's where your tension is greatest. So like if your rope's going to break, that's where it's going to break, right at the bottom. Now for this one, you need to remember my counterclockwise, clockwise. Counterclockwise is positive, clockwise is negative. And then all those things about acceleration and velocity are still in play. So here I have a negative omega. That means that it's traveling in the clockwise direction. And it says it's speeding up. So if it's speeding up, that means I have a positive alpha. Or, no, I'm sorry. I have a what? I have a negative alpha. The velocity and acceleration are in the same direction. All right. Do you have another one? Okay. Any more questions? All right. Y'all hang in there. We're almost done. I know an hour is a long time to go. But if you need to go, that's fine. You can leave. Let's look at quiz 5. All right, which of these? There's a lot of stuff on this. You're not going to see every topic that we covered, but you'll see quite a few of them. Number 7. Okay, this was straight from the concept test. Listen, when you have this block of wood, it displaces a certain amount of water, right? They're right up to the top. And it displaces a certain amount of water. The water that it displaces is equal to its weight. Because, I know this because my buoyant force is up, my weight is down. And the buoyant force is equal to the weight. Because it's floating, it's not sunk all the way down to the bottom, so the buoyant force is equal to the weight. It's enough to cause it to float. And the buoyant force is equal to the weight of the displaced fluid. That's Archimedes' principle. And the weight of the displaced fluid is equal to the weight of the block. So you put the block in, but you also lost the weight of the fluid, and those two are equal because of Archimedes' principle. And so you put the block in, you lose the same amount of weight in fluid, and so they have the same weight. If it would be the same if it was in the middle, right. If it was on the bottom, it wouldn't be the same. Right. And if it was on the bottom, beaker B would be heavier, right? Because it's not displacing its weight in fluid. Bye, Holly. See you next week. All right. A lot of people miss this one, and you're going to kick yourself. Okay. It's not the area, it's the radius. Well, area is pi r squared. But you didn't really need to know that. Like, you could have just said the radius squared. Like, you could have treated it as a square because the pi would cancel out. But you had to square that radius. Y'all should know the area of a circle. Like, that's something you use every day. What is it, pi? Oh, because I have F1 over A1 equals F2 over A2. F1 is 15,000 over pi 0.2 squared. See, the pi's cancel out. I can just multiply both sides by pi, and they cancel out. You didn't really need to know the area of a circle, but you did need to know that the area was proportional to the radius squared. But you know, everybody knows that. You just weren't reading it carefully. You need to read these things very carefully, okay? Yeah, we had a problem like this, I think, in the homework, or in one of the quick test questions. I have a pipe like this. It gets bigger like that, and I want to know what is the flow in the second pipe. It has a lot of information, but you don't need any of this. All you need to know is the radii and the flow right there. So I use the continuity equation, A1V1 equals A2V2. A1 is 0.5 centimeters, that's my radius, squared, times pi, times 6, equals A2, pi 1.5 squared. I'm sorry. I think that on most of these, I don't have these little extra calculations that you have to do. Like, this is like a little extra calculation you have to do. I think on most of the final questions, I don't have that, but you might see it sometimes. Just be very careful when you read it. Take that extra 3 seconds to read it again.
Well, I noticed that this wasn't the area, but then we didn't have any more information to figure it out, so I figured it would be okay.
It wasn't, yeah. Good. All right.
I still wrote down what I... Well, I'm trying to figure it out because I realized that one radius is 3 times the other one.
Right. So it's going to be 1/9. Since the radius increases by 3, the velocity goes down by a factor of 9.
Yeah.
So it's 6 over 9, which is what, 0.67? All right, what else? 15. Yeah, you had to use Bernoulli's principle, which I know is kind of daunting, but it actually worked out to be the math was pretty simple. Bernoulli's principle is P1 V2. Remember, Bernoulli's principle is based on the conservation of energy. The equation of continuity is based on what? Conservation of matter, right? That if you have a certain flow of fluid going through a pipe, that same amount of fluid has to go through a smaller pipe. Bernoulli's is energy. Continuity equation is the conservation of matter. Did I get that? Matter. Did you hear me? Matter. Bernoulli's equation is based on the conservation of energy. The continuity equation, one pipe, new pipe, is the conservation of matter. That if I have a certain amount of matter going through a pipe, that same amount of matter has to go through the second pipe. So it has to go through faster or slower, depending on the volume. Rho V2 squared. All right, now some of the things here cancel out because the pressure remains unchanged. So I can subtract P from both sides. It goes 3 meters higher. That means that H1, we're going to take to be 0, and H2 will be 3. Now I can also cancel out all these rows, because I have a row in every term. Since the pressures went away, I can divide through the whole thing by row. It doesn't matter. You don't have to cancel out the row. It just makes your math a little easier. But you cancel what? Uh-huh. Mm-hmm. No, but what you can divide through. This is what you're doing. You're just dividing through the whole thing by row. And you can do that if you do it to all sides. And then it gets rid of the row in each term. But only because this pressure was no longer there. Because there is no row in the pressure. All right. So if you had the pressure, you couldn't do that. Because then you would get like P over rho, which doesn't make any sense. All right, so I have 1/2 V1, which is 15 squared, equals 1/2 V2, which is what I'm looking for, squared plus 10 times 3. And then I solve for V2. I'll let y'all to do that. Now, Bernoulli's equation, it seems a little daunting, but I'll try to make it simple with the math. Because next year, I'm going to do no calculators. Not in the spring, next fall, I think. Jared? Huh? No, you can't cancel. Oh, yeah, I didn't put in. Right here? This went away because H is 0. Right, so H is 0 here, and H is 3 here. Because it goes 3 meters higher, I take H1 to be 0, and then H2 to be 3 meters higher. I could have said this is 6 and this is 9, but I make it 0 and 3. All right? Is that clear? What else? Okay, I think I told y'all here that the buoyant force was what, 55.9 or something? Yeah, 55.9. You won't see apparent mass, apparent weight, so let's not worry about how I got that. But now I want to know the density of the rock. I say the buoyant force is equal to the density of the fluid times the volume of the displaced fluid, which is equal to the volume of the object. So the object displaces a certain amount of fluid, and that's equal to the volume of the object times G. And so that was it, really. 55.9 equals to 1,000 times the volume of the object Oh no, I had another step to it. Times 10. That's 55.9 over 10,000. Oh, yeah, so it's 0.0056 cubic meters. And then I want to know the density, because mass over volume. That's the density of the rock. So now I know the volume of the rock. I just take its mass, which is 9 kilograms, divided by this 0.0056, 1600, yeah, 1580. All right. Right, I told y'all that there was no apparent mass, and that's why I gave you the buoyant force there. So you really didn't need this stuff. All right. Okay. A lot of people missed this. I didn't put it on there. So, let me show you, because you could see the ideal gas law, but PV is equal to nRT. And if you read the problem, I could have two 1 liter containers, so they have the same volume.
Volume, molar mass, they know they're going to have bigger weight. Inverse relationship between volume, pressure, and volume always has an inverse relationship. You know what I'm saying? I guess I understand we said 2 liter, 1 liter.
Mm-hmm.
They understand, like, yeah, that's you're setting the volume, but I guess I was thinking internally, the volume is different.
No, because
You know what I'm saying? Like,
but a gas always takes the volume of its container. That's a gas for you. Okay. But they have the same volume, they have the same number of moles, and they're at the same temperature, so they have to have the same pressure. I know it doesn't make sense because you have more mass of the oxygen because it has a greater molecular mass, but you still have the same number of moles, which is the relevant thing here. All right. A lot of people miss this one. Yeah. Right. Oh. Yeah. What is it? I forget what U means. But it's a unit. I think it's just grams per mole. No, it's something else. I don't know. I'm not a chemist. Something like it's not relevant. It's not on there. Everybody and their sister missed it. What else? Oh, yeah. Okay, this was a basic ideal gas law. Just putting in our thing, you have to check the units. So 1.5 atmospheres is 1.5 times 10 to the fifth. My volume is 0.1 cubic meters. N is 10 moles. R is 8.314. And then T, you're solving for T. And then you get T, gosh, what was it? It was 180, right? But it's in Kelvin, not in centigrade. And you can know that because if you look at R, I told y'all this in class, all right? You have to be careful with your units. It comes up in SI units, which is Kelvin, but I'm looking for it in Celsius. Usually if I bold and italicize something, that's an important part. And I try to do that, like especially if the problem is very similar to the quiz questions, I'll bold and italicize the things that I've changed if it's very similar, so that just make sure you take notice of those things especially. And then if you convert this to Kelvin, it's what? Minus 93. I mean, if you convert it to Celsius, it's minus 93. Your conversion equation is on your equation sheet. Right. Because 180 is there, right? You get to that answer like, woo, I got it right. That's kind of mean, isn't it? But that's the way they write. But that's the way these tests are. I mean, they're all this way. So. All right. What else? And I'll stay here and answer questions as long as you have. But I just want you to know we usually eat right about now. And I got up at 2:30 this morning, so. Yeah. I'll answer more questions. That wasn't a this is the end. Yeah, in the auditorium. There's seating. I've already put up the seating charts over there. I'll answer more questions. You have more questions? You'll have 2 hours, 7? Yeah. I think it should be just enough time. I'm sorry. Yeah. Anything else, guys? Good.